Good afternoon, guys. So this week we will start multi-class classification. So we worked with binary classification um, 2 previous weeks, and this week we will move to the multi-class classification. So expecting one student on Zoom, but there is no one for now. Okay. Um, Dexter. Thank you. Um, so yeah, we worked with two label classification or binary classification, and we derived formula for binary cross entropy. Today we'll derive formula for cross entropy, not binary, general. But before we go into this logistic regression for multi-class classification, let's think about the problem itself and the metrics. So um, we have three classes in this example, and uh, how can we actually classify a new point somewhere on this plane as class blue, yellow, or green if we know our previous methods? So can you think about how can we use one of the previously learned methods for classification in case of multi-class classification, 3 classes? For example, yep.
Classify one that's either purple or not purple.
Yes, and this is the approach which is called one versus all. You can consider one class, for example, this blue purple as class 0, and other classes as class 1. It will be binary 1 versus all. Can we use k-nearest neighbors for classification? We also can um, um, classify a point based on the closeness. But I want to use binary linear classification, not k-nearest neighbors. Yes.
Could we do 2 lines instead of one, and then it would just sum the ones and zeros after
Yes.
classes?
Yes. So this is called teapot principle. So when we want to use something that we learned before to solve a new problem. And there is a joke that mathematicians and physicists were asked a question, how to boil water if you have a teapot and a stove. And physicists answered that you should put on in the water and put the teapot on the stove and switch on the stove. The mathematician replied the same. Then they were asked another question. If you have the full teapot on the stove, how to boil the water? And physicists said, just turn on the stove, while mathematician replied that you should first empty the teapot and then you will reduce your problem to the solved one. So when we want to use something that we actually solved before, this is the name teapot principle. So we will use the binary classification to solve the multi-class classification. And as could you remind your name, please? Aiden, as Aiden said, and also, and what's your name? Paul. So you both were correct. One option is to use one versus all when we consider one class as one class and all other classes as another class. In this case, the number of lines will be the same as the number of classes. Was one versus all. So for every class, we will build a decision boundary. And for example, for this class, purple, green, and yellow will be the second class. So this will be the decision boundary. For class green, we will have this decision boundary, which will try to separate green points from other points. And for yellow class, this green line will separate the yellow class from other classes. How to assign actually the class to a new point? So let's go first for example, and then we will go back to the formula. So we want to classify the new point, the red one. So we built three classifiers. Let's see. So there are numbers. You can see there are numbers. So we built three linear regressions. In this case, logistic regressions, I believe. Yeah, because predicts proba. And first, we return the probability of this point to belong to blue class, and the probability is 0.99. Then we built another linear regression when we compare this green class versus all, and the probability that our point belongs to green class is 0.03. Then we built another linear function, the green one, and we return the probability that our point belongs to yellow class. And this probability is also very small, 2^-6. And based on these numbers, we make our classification that our point belongs to class, the first class. And here is the formula. Now you will understand it better. For each class C, we build a linear classifier, or maybe not linear, just some classifier. And then based on the returned value, which can be a dot product or probability, we choose the index, and this index we assign as the class to our data. So we choose the classifier with highest probability or highest returned value. The second approach is called all versus all. So let's again look first at the image and then look at the formula. In all versus all, we build all possible pair classifiers. So for example, on the first line of this matrix, I will build two classifiers with labels 0, 1 and 0, 2, which corresponds to classification between purple and green and purple and yellow points. So between purple and green, the classifier is this blue line, and based on this classification, red point belongs to blue class. And if we count from 0, then we return class 0. For the second classifier between purple or blue and yellow, we have another decision boundary. And again, this point is classified as the first class. So we return label 0. Then we build a classifier between classes 1 and 0. But it's the same as between 0 and 1. So again, we return class label 0. Then between classes 1 and 2. Between classes 1 and 2, between yellow and green points, this line will be our decision boundary, and the red point will classify as class green. So that's why we return label 1 here. If we label our classes 1, 0, 1, and 2, so we will classify as green. And then we build binary classification between classes 2 and 0, but it's the same as between 0 and 2, so this metric is symmetric. And in the end, we just count how many classifiers classify this point as class 0. In this case, 4. How many classifiers classify this point as class 1, 2, and how many classifiers classify this point as class 2, in this case 0. And we assign the class by the more frequent class in this table. And this is the formula. Your drones. Now, I think it's easier to understand. For every pair of our classes, we build a classifier. And in our case, it's just the number of combinations. If we have 3 classes, then we have 3 combinations, like purple versus green, purple versus yellow, 2 combinations, and yellow versus green, the third one. And you remember the formula is n factorial over n minus k factorial, the total number of combinations. So we build this all combination classifiers, and then we count how many classifiers classified our point as class 1. So this is the sum. Then how many classifiers classify this point as class 2? How many classifiers classify this point as class 3, 4, and so on? I will stop here. And then we choose the class with largest sum. So, okay, now let's talk about metrics. We know metrics for binary classification, for true positive, true negative, false negative, false positive. How to generalize these metrics to the case of multi-class classification? There are 2 approaches. One is called micro-averaging, another is called macro-averaging. Of course, you can use accuracy. Accuracy just how many correct guesses. It will be unchanged. But how to build a confusion matrix in case of multi-class classification? Let's talk about this, because confusion matrix has just true positives and false negatives. It was built for binary classification. The answer is that we will build confusion matrix for every class. For example, we have class C equals 1. And we will to call true positive point if it was classified as class 1 and true label was class 1. And we denote this by true positive, with index 1, for example. By true negative, we will mean all the points that our model classified as different class. It doesn't matter which one, but not class 1. And the label also of that point was different from 1. So this is how we use kind of binary idea multi-class classification, and we will call this true negative 1. Then we will build this matrix for class 2. So we will calculate how many points with true label 2 our model predicted as class 2. And we will denote this true positive with index 2. And if our model predicted the point by a different class and the label was different, they shouldn't coincide, just different from 2, then we will call this true negative. And we can calculate these confusion matrices for every class. So C goes from 1 to C capital. We have C capital classes. Then we can calculate C matrix, true positive, false positive, and so on. Then there are two ways. That's why we have kind of two formulas. You can take the and sum up all true positive values for all classes and use this like aggregated value in the formula for precision. The other option is to calculate precision for every C. First, to calculate precision for every class. So for precision for table 1, precision for table 2, and then return the average precision. Let's think about the differences. So what if I have a very small class, underrepresented class, for example, with just 5 points and other classes with hundreds of points. What can you tell about the final precision if in numerator we just use the sum over true positives over all classes? Will it actually detect that our points from this underrepresented class were classified incorrectly? No, because the main impact will be from the largest class in this case. So this is this formula is not sensitive for unbalanced classes. So it will just represent the greatest class in your data. Let's think about macro averaging. For example, our model misclassified all points from this underrepresented class. It means that precision with index 1 will be 0. And when we take the average, here we divide by the total number of classes. This actually metric will be smaller if our model made mistakes on even very underrepresented class. So this metric, macro averaging, is more stable for unbalanced classification. And maybe you remember in your output from metrics in homework, it also prints micro. So now you understand what does it mean micro, because we had binary classification, but even for binary classification, you can use macro, micro averaging. Okay, I think that's it about quality metrics. Now let's, if we have time, we will talk about unbalanced classes. For now, let's go to our problem solving. And we will look at the problem, which actually classifies all classes, not binary classification, but multi-class classification, and this is called logistic regression, but multi-class logistic regression. So in this case, we don't need one versus all or all versus all. It will learn classes just from the data without using a teapot principle. So let's look at the first problem. So as you remember, in binary logistic regression, we had probability of our y target equals 1 given x, and probability of y given of y equals -1 given x. And we used one linear function, and then we used logistic function, sigmoid function, that transformed this linear function into probabilities. So here we had weights times x. And tilde because we allow to have bias, so our classifier. And the probability of negative class, we calculated as 1 minus probability of the positive class. Now let's think about another approach. Instead of using one function for both classes, let's introduce two linear functions, like here. One linear function and another linear function. So one linear function, we will use the first index for class 1, and here the first index for class 2, and so on. Let's introduce, now for problem 1, we'll talk just about two classes. So we'll introduce two linear functions, so twice more parameters. And how to convert this into probabilities? To convert this into probabilities, we will use this formula, which is called softmax. So we will assign the probability of class 1 using this formula. So it will be W1 transpose times X, and probability, and the denominator will be just e to the power W1 transpose times X tilde plus e to the power W2 transpose times X tilde. So this is just preparation. We didn't start the problem itself. So, and for class -1, the probability will be the same, but in numerator, we will have exponent power W2 times X. And I hope you can see that if we sum up these numbers, you will get 1. So our general goal is to convert linear functions into probabilities. And the same denominator. I'm lazy to write the tilde. and transposition, I will just use the dot for product. Okay, I hope you agree that these numbers will sum up to 1. So, okay, and after that, when we converted these linear functions into probabilities, we can calculate the joint probability, which is called likelihood. And then we maximize likelihood, then we use negative sign, and we get loss function, which is called, in this case, cross entropy. So last time we learned binary cross entropy, and it was log of 1 plus e power margin. Now we will learn just cross entropy without binary. And in machine learning, we have two main functions, MSE loss and cross entropy loss. Binary cross entropy loss is just a particular case when we have two classes. So let's write down the probability. I denote the first, in this paper work, I denote the first probability by P with index W1, because it depends on the weights with index 1 of X, because it also depends on the point X. Here's the linear function. And the second probability I denote by PW2 of X. So what is the probability? Let's write down the probability that our point, a random point, has label yi, and this, in my case, yi can take values 1 or -1, given the point features xi. So I will write down, and I hope you will understand why it's the case. So it's the probability that our point xi belongs to class 1 to the power I'm using Iverson brackets, yi equals class 1 times probability of class 2 that our point x with features xi was classified as class 2 times the Iverson brackets that true label equals -1. That true label equals -1. So let's think about why this formula is correct. So if the true target equals 1, what is the value of this bracket? Is it true or false? If true target is 1, it's true, and then the value will be 1. And we will get just the probability of the first class. What about the second bracket if the target is 1? It's false, so it's 0. And any number power 0 will be 1. So for class 1, if y lowercase equals 1, this formula results in probability of the first class. So if our y is -1, then this will be 0. And this will be 1. And we will get probability of the class negative. So, but we can use now this notation and write the joint probability for all the points. So likelihood function, likelihood function, L, that now depends on two parameters, vector parameters W1 and W2, is the product of these probabilities for all the points from 1 to n. And I'm lazy, just put this here. So this goes to the product. So we'll have the product of the probability for individual point with index I. As you remember, we don't want to work with product. We take logarithm and we will get log likelihood. So and we, as you remember, we maximize this with respect to these parameters W1 and W2. Then we take log likelihood, log of this L. The product becomes the sum, product of logarithm of product is the sum of logarithms. And under the sum, again, we'll have the log of product, and I will split this into sum of two logs. So it will be, and the power will go out, yi equals 1. Times log of the probability of the first class. It depends on x, but maybe we can skip it. Okay, I will write depends on xi. Plus the second multiple. Again, the power will go outside the log. Yi equals -1. And times the log of the second probability of the second class. And we want to maximize this sum. To write the loss function, we will just write negative sign and minimize. So this is the solution for problem 1. The loss function the final answer. Sometimes this loss function is called log loss, but it's just because it's the negative log of the likelihood. So it's a negative. We also add factor 1 over n times the log likelihood. And just substitute instead of log likelihood this expression. Log of L. So just substitute log of L here. And we want to minimize this because it's negative. Minimize. And this is called cross entropy loss with respect to our parameters W1 and W2. So what's the difference with our binary cross entropy? The difference is that now we have twice more parameters. Instead of just one linear function, now we have two linear functions. And when we have a lot of data, then we can learn a lot of parameters. So you want to use the first approach when you just calculate probability for one class and use 1 minus this probability. When you have a small amount of data, and that's why it's typically used in statistics. And in machine learning, you can learn more parameters if you have more data. So you just represent each probability as a function of these parameters, and then maximize this, this joint probability. And in this case, this function is called cross entropy loss. So if you think about this function, you will notice that only one of these terms is not zero, because true label is 1 or negative 1. So at least one of these terms will be 0. So an easier way to write this function is an easier way, an easier representation is the sum over all points so you don't need to do this. If I will use instead of class 1 and negative 1, 1 and 2, like, I mean, it will be just easier to write the formula. Then here I can write the log of P with index W, and index of W will be my label with index yi of x I. Carton, you don't need to write this formula because it's kind of a little not really not related, because in your assignment we have classes 1 and negative 1. But if we would use labels like 1, 2, 3, 4, 5, 6, 7, and so on, then the index of my weight W would coincide with label. And then in this formula, instead of using two terms, I could use just one term, and which corresponds to a true label. Does it make sense? So yeah, this is the easier formula for cross entropy. Okay, so now let's move to the second page. I hope you can prove that this number sum up to 1. For problem 3, you just copy paste from problem 1, but instead of classes 1 and -1, you will have classes 1, 2, 3 up to C. And problem 4, I will solve with 0. Yeah, feel free to communicate or ask questions. Again, it's the most used loss function. So I just want you to understand this function better. So yeah, and the formula in blue will work for problem 3. So actually, this is you will have this as answer for problem 3. Because the yi will denote the true class, and then you will have kind of C terms. From these C terms, only one will be not 0. Is that X? Yeah. Yeah, it looks ugly from the first glance, but if you look at the final formula, it doesn't look ugly. So for problem 3, it would be nice if you would write the formula for probability. You will have C terms, then take log, you will get this formula, and finally, because only one term will be non-zero, it will be simplified. So for problem 2, it's easy. So for problem 2, you just want to sum up the numbers p, and each number p is the exponent power a with index c over sum a with index. If you want, you can use another index k. And the sum of the fractions with the same denominator will be the fraction with the sum, and the sums will cancel out. So that's a straightforward problem 2. Just prove that these numbers sum up to 1. For problem 3, just add more terms for classes. Yes. Yes, yeah, it's correct. And then you can just notice that only one of these Iverson brackets is on zero. And the only one which is not zero, let's say your y true label is 2, then only this bracket will be not zero. So you can use here index y. Yes, and then you will get, instead of this sum, you will get just one term, but the index will correspond to the true label. If you have any questions, feel free to ask. Yes. No. So, no, it would make so first of all, we sum up all the points. Yeah. All of them. Then it would make sense if you would write here C and sum also over C. But then you should notice that only one bracket will be non-zero when C equals actually y out. And then you will get here. Just then C will be replaced with y. And this will be one. And then, okay. Does it make sense? Yeah, the problem 4 is more just to understand why this formula is called cross entropy. So I will solve it with you because it's just the notion from probability or information theory. So we have 5 more minutes about that. Then I will explain problem 4, and we will have I also prepared illustration from the last one. Yes, current. Yeah, yeah, great. And then the only plus, which is white I will be on zero, so that is here, it's still log of P with index white. On all this term, only the term with plus C equals by I will be on zero. So you just replace this upstream with white. So you will get the probability of weights, and the index of weights will be by us. Why the index? Oh, W2, index. Because this is the truth. Yes. Oh, I think this is, I'm fine with that. Okay. But or the professional football. I mean, it's best. It would be nice if you would just write this and the sum in the numerator to show that statements were. Because the common denominator in sum. So
Numerator and denominator are all same value, so it's just gonna be one.
and okay, so
Like, the sum of all these terms, is this term. So if you add all the numbers, you get one.
and
Yeah, because this is C, it doesn't depend on which index you're using. You know what I mean?
right.
So this is the same denominator for each term. And then the sum of each of these. No, well, like when you sum these, you're summing it, right?
Oh, right.
Yeah.
Yeah, it's all nice. So you just do. Oh, okay.
It's because, yeah, the only, is there script like both clauses. Yeah, that's.
I forget math. It's a lot.
For J equals by I equals by 1. So it's not.
I mean, I feel like from
Oh, yeah, because the event.
That's what the.
I got.
Oh. I'm.
That's the answer.
Yes.
How would you like explaining?
Would make sense.
Well, just like for my position.
No, it's fine
I mean, it's just the sum of all numbers.
because
Oh, I'm talking about two, sorry.
oh, two. Well, for two, just one more. Just one more step.
What's that?
The sum of fractions will be the fraction of the sum. And then it's cancelled out.
It was, but for this, it's.
Great.
Yeah, you do that and that's.
So, and then, this bracket will be non-zero. Only when
Yeah.
J equals Y.
Yeah.
So-
Oh,
And the. It should see the whole plus now.
yes.
Yeah, so this sum will be reduced to J equals Y.
Yeah. Yeah, exactly. So,
And you will get this rule.
yes.
So there's 3 on here. It's the same as this, but let's see, instead of N.
Nice.
So.
I can write that for the message.
Oh, okay, so it's here. So,
This will be.
yes, now you take the log. So it will be sum over I and sum over J.
Oh, yeah.
This will go around.
So where what is these things to the constant J. Is
Times the log.
So then
Outside of the song, so it's the exact same song.
Both bound to your C.
No, the first is over points, the second over classes.
Yes, logically,
Because this is the product for 1 point.
all the points are.
And then just notice that
It's the.
this bracket will belong to 0 only when J equals I. So the J substitute with Y. And you won't have the second sum. Sorry, is your math?
I think it's okay. I didn't write a double summation here just because I just had
So,
this one will do another summation.
So This is the problem.
And that
Oh, yeah.
just.
Then you take log,
But like.
it becomes the sum.
Like, but I, so this is very. Like, this is a.
Because it's a plus one.
Okay, yeah, I do have C here,
Yes.
so that, okay, that makes sense.
Yeah.
It's not-
And finally,
The other all the negative and one.
for only one term will be non-zero when C equals yi.
It doesn't even matter.
So that's why we'll have W with index.
And is this supposed to be negative or not?
Yeah, because
That's-
we maximize this and we minimize it.
Because.
Okay,
it-
thank you.
I assume that.
You're welcome.
Yes, the person who is that.
Okay, so can we go to the last problem 4? So, for problem 4, let's talk about cross entropy. Problems here. So, let's start with definition of information. Then we will give definition of entropy, and then we will give definition of cross entropy. So it's again just to give you some idea why this loss function is called cross entropy. It's not important just that you solved it, so I will solve it. Let's think about the tossing coin and which results in head or tails with equal probability 1/2. So do you remember how the information is defined? For example, of the distribution with probabilities p, how the information is defined in computer science or statistics. It's negative log of p, negative log. And in computer science, we use base 2. In statistics, typically we use natural log. So what is the information if you flip a coin and it resulted in heads, for example? How much information will you get from one bit of information? Just substitute 1/2 for p. It's 1. So it's 1 bit. So what if our coin is completely biased that, for example, we always get tails? The probability of heads is 0. What will be the information in this case that tossing resulted in heads? Well, probability of log of 0 is in case of information, we just by definition say that log of 0 is 0. But for example, for 1, if your tossing resulted in tails, the information will be 0. There is no new information because we know that every time we flip a coin, we will get tails. Does it make sense? So entropy is the average, or expected value of information. Entropy is the expectation of information. expected value of information. And let's calculate, for example, entropy for the unbiased, for fair coin. As you remember, and expected value is the probability times the function of the random variable. So in this case, it will be 1/2 times log of the first probability, which is 1/2, plus the second probability, which is again 1/2, times the function of the second probability. So what is the negative? Sorry, information is negative, log negative. So yeah, what is the value? 1. So if you calculate this for biased coin, it will be 0 times something minus 1 times log of 1. And you will get log of 1 is 0. You will get 0. So in entropy, maybe you know, it's kind of the measure of uncertainty or of chaos. And in case of the highest uncertainty, the uniform distribution, the entropy is 1. And in case of the lowest uncertainty, in case of certainty, the entropy is 0. So cross entropy is the measure of similarity between two distributions. So cross entropy has 2 parameters. In case of, so it's the expected value of the information, but when we used one dictionary to encode our sequence and a different dictionary to decode the sequence. So in other words, how accurate can we decode a sequence with with a dictionary with M words when the input sequence was encoded with the dictionary which used another number of words? So and let's look at this formula. So in place of P, we will use our probability of Y from problem 3. And probability of Y, as you remember, was PW1 for 1, PW2 for 2, and so on. So that's why here we have this log of PW1, log of P subscript C. The distribution that we will compare with is the true distribution of data. And if our data point had class Y with yi, then the probability that our point had another class is 0. So it's just kind of one hot encoder for our data. And that means that the probability that our random variable, I denoted this by Z, like one hot encoded, is the same as Iverson bracket yi equals 1. And so on. The probability that the probability that truth label is C is the same as yi equals C. So if you compare the function from problem 3 with this function, you should notice that they are equal. So it just to explain the term cross entropy loss. Why it's called cross entropy loss? Because it has connection with definition of cross entropy. Oh, equals C, so sorry. So just by observation, you can say that the cross entropy between target Y and true labels Z is the same as the loss function that you derive in previous problem. Does it make sense? I just hide one more step, that there is the randomness in our data is typically in the index. The randomness, like you remember in gradient descent, we choose randomly I a data point. So here the randomness is also in the index. So we should also take so this is actually called conditional expectation. But to calculate the full expected value, we should also take the expected value with respect to index I. And when we take the expected expectation with respect to I, we assume that probability of every point is 1 over n. And here's where 1 over n actually comes into play. So finally, we also take the expected value with respect to I, and we will get sum. The probability for every point I will be 1 over n. And then we have this cross entropy for point I. This is called complete expectation formula. When we calculate first expected value with respect to I, and then we take expected value for I. Okay, now I have prepared illustration. Don't forget to sign your papers. Yeah, okay. So machine learning 13. Well, again, there are only two loss functions that you will use in, for example, neural networks, MSE loss and cross entropy loss. Well, there is also binary cross entropy loss for binary classification. So I just want you to understand their names and how they work. Of course, you will use this from a box, and you wouldn't care about gradient descent, but it's good to understand the difference that binary cross entropy works with one linear function. Cross entropy works with the same number as the number of your classes. And let's look at the notebook. So this is how I created the images for the presentation. Then I feed the logistic regressions, free regressions, and used intercepts to plot these lines. So then, yeah, the predict prober. This is for one versus all versus all. Okay, now it's the interesting part. We will call the logistic regression, and logistic regression has these parameters which decision boundary you will use. One versus rest, which is one versus all, or multinomial is our logistic regression that we just solved now. Auto, I don't remember which is auto by default. Let's try. So if we use the one versus rest, one versus all, the decision boundary is looks like this. If we use, I believe default is the, I hope default is the multinomial. Let's see. Yes, so can you see the difference between the logistic regression when we maximize probability and logistic regression when it trains just 3 linear regression, binary logistic regressions? So can you see the difference? Which one do you think is better just for this data? Huh?
Which out of the three?
Let's see. I was thinking that default, I believe multinomial is default. Oh my gosh. It's the no, I think this is better than the previous one. Because it kind of leaves this region classified as middle class. And it makes sense because in logistic regression, actually, we maximize the joint probability in case of one versus rest, we just build 3 independent decision boundaries and then make the decision. And you can use this to handwritten digit recognition. So you can upload data set MNIST, which has 8 by 8 numbers, and apply the logistic regression, train logistic regression, and get the accuracy. And you remember we told today that macro accuracy is better, but our classes are pretty balanced, so you can use just accuracy, and the accuracy is 96%. So I think it's compared with human accuracy for digit recognition because we can fall asleep and classify incorrectly or something else. Okay, so, and if you look at the output, so the last comment for today, the output is 10. And if you look at the individual weight, individual weight has 8 by 8 parameters because it creates 10 linear functions, and every linear function will have 8 by 8 weights. Okay, so that's it for today. I'm glad that we at least covered also example. Yeah, with your papers. So next time it will be code, so you can stay home.
Oh, it's like that much of a difference.
Yes.
I kept staying home just because I wasn't 100% from being sick. So,
Yes.
so that's why I'm back now. But I just wanted to wait until I was 100% down.
No, but I know that you drive and then back.
Yeah. Thank you.
You're welcome.
Have a good one.
You too.
Like,